Okay, we know that kinetic energy is half mv squared. So EK, oh, wrong colour, hang on. EK equals half mv squared. Okay, now what velocity formulas do we know? We need to put something in there, don't we? We know mass is pretty straightforward, you just get it from the thing, but we want to know velocity at any time or at any displacement. So we know one from previous, V equals plus minus omega square root a squared minus x squared. Now, if we substitute that in, you then get EK equals half m omega squared a squared minus x squared. So we could put that in as our formula. You know, we know that, hey, when does kinetic energy max occur? It's actually when the displacement is 0. Okay, so 0, so max when 0 displacement. Okay, so we can actually say that kinetic energy is equal to half m omega squared a squared. That's max. Okay. Now, the maximum value of this kinetic energy should be equal to the total energy of the system. Okay, in other words, if you think of a pendulum going back and forth, okay, so it swings along at different positions. As it swings back and forth, then it's just swapping energy between kinetic to potential, back to kinetic, and so on. Okay, so it's just swinging back and forth. Now, there's no energy lost in the system in this case. Okay, so we're saying that all kinetic energy is transferred to potential, and all potential is transferred to kinetic. So because there is the conservation of energy, that's why this happens. So now we look at, well, how do we calculate potential energy? So potential energy will be equal to total energy minus kinetic energy. Now we know that from before, the total energy is the maximum kinetic energy. So let's put in the maximum kinetic energy and take off kinetic energy at any time. Now, expand all that out. A lot of omegas and squares and things, so okay, so expand all that out. Simplify, and you get potential energy equals half m omega squared x squared. Now, so if we actually looked at a graph of this, and we had an object going up and down with a displacement x, and we graphed energy first, that displacement, so usually it's in something like millijoules, then the kinetic energy is max at 0 displacement, and then as some sort of value to the amplitude, and minus amplitude, you go to 0. And it's x squared, so it's got that relationship, or amplitude squared. The other way is potential energy. So potential energy is 0 at 0 and maximum at the amplitudes. Okay, and so it goes around like that. And at all times you get to a maximum. Do not exceed the amplitude. Okay, the line should not go further past that. So this is EP. This one is EK, and we should put another line maybe for the total energy. Oh, why is it there? It's a bit silly. Let's do it properly. Oh, if I can get rid of it. Hang on. Let's rub it out. Let's try again. What am I doing? So, the total energy will stay the constant, and it must be equal to the maximum kinetic energy and potential energy. So really those green things should stop on the line there. Okay, so this is the total energy, and it stays constant. Now we know that it won't actually stay constant forever. We know that this energy must reduce over time somehow, okay? And if that ever does happen, you have to keep the shape of the graph the same. Okay, so the shape stays the same. And so if that total energy did reduce over time, you get this new graph. Okay, so you get a new amplitude and so on. Okay, so be aware that's how you should look at it. Well, that's quite confusing now. Why do we lose energy? It's because of this thing here, damping. All oscillations will lose total energy to dissipative forces. This will reduce the amplitude and maximum height of the oscillations. Dissipative forces work to slow the motion, and they come in the normal stuff, friction, air resistance, viscous drag, eddy currents. There's a few other ways. The greater the degree of damping, we've got different names for it: light damping, heavy damping. So heavy damping, essentially there's only one oscillation. Okay, light damping, there's many oscillations and you can get varying amounts, but you notice that the period still stays the same. So the frequency of the oscillation will not change with damping unless the resonant conditions are changed. Okay, resonant conditions to do with this natural and forced frequencies of vibration. Now anything that you make, if you build the Sky Tower, okay, it will oscillate in wind with a certain frequency. Okay, pretty low frequency, probably something like 4 Hertz. Okay, or much lower, maybe 1 Hertz. It will oscillate with this frequency. A pendulum oscillates with one frequency, and that's dependent only on the length and gravity. Okay, so you do it on the moon, you'll get a different resonant frequency. Do it with a different length, you get a different resonant frequency. However, change the mass, no change. So these things are called, natural frequency. So you build a bridge, okay, across a river. It will oscillate back and forth, maybe with a natural frequency. Okay, so that's where people get scared about people running across bridges and things. If everyone runs in time, you can create a resonant effect, or where the energy will build up. So if the object is being pushed at periodic intervals to either help or hinder the motion, is called a forced frequency or forced oscillation. So think of a swing. So let's say we had our swing. Here's a person sitting on the swing. Okay, and if you keep pushing them, so there's another person here pushing. Funny looking person. If that person keeps pushing, then it can increase the energy. In other words, the amplitude will get larger. Okay. Now, if you think about this, you only really push when the object is in the downward cycle. Okay. So you're actually pushing in time with the natural frequency. Okay. And if you do that, it will increase energy. However, if you pushed as the thing was coming towards you, you will reduce the energy. Okay? So you have to be... So what's happening here is we're saying that we're forcing the oscillation in time with its natural frequency will increase its energy. However, if we push it out of time with its natural frequency, then it will reduce energy. And so we can graph it here. We can see that we have our natural frequency along there, okay, and if you move the frequency of forced oscillation outside of it, this way or this way, then that amplitude will not be as high. Okay, it will not increase energy, you'll lose some energy. So what happened to the forced oscillations if they match the natural frequency and there was no damping? Well, every time you imagine you push it, you put energy into a swing, okay, with a force, okay, and the energy will not dissipate from the swing. So you keep putting energy in. Continue energy in. Okay, and that means it will keep going so you get an infinite amount of energy. So it's not really possible, there's always going to be damping. What about if the resonant frequency is half the natural frequency? Let's say you're trying to push a swing with half the natural frequency. Well, in that case, it's actually you're right. what it is you're actually going to push it every second oscillation in time. So it will actually increase its energy, but nowhere near as much as pushing it every time in time. If you started pushing it at twice the natural frequency, then you start pushing it when it's coming towards you. Okay, or when the swing's coming towards you, so you start pushing it out of time, and that makes it worse. So that's referring to the resonant graphs, which look like that. So double the frequency is worse than being half the frequency.